Donc d'abord, je voudrais commencer par quelques mots pour Denis. Ce que je voudrais mettre en lumière, c'est le rôle que Denis a joué dans mon développement de carrière à Nice. En fait, si je suis à Nice, c'est pas par hasard. Donc Denis m'avait mis en contact avec le laboratoire de mathématiques de Nice. Bon, suite à cela, j'avais été en position d'accepter le poste, mais il est certain que s'il n'y avait pas eu l'équipe Tosca à quelques kilomètres de l'université, probablement j'aurais pas accepté. Et durant les premières années de ma carrière à Nice, j'ai été très très heureux d'aller régulièrement à Tosca. J'ai eu des collaborations dont je suis très très content sur des modèles de Makin-Vlasov avec des singularités inspirées des neurosciences, et Denis nous poussait à aller dans ces directions-là. Et pour ça, vraiment un grand merci. Et je voudrais aussi dire que j'avais bénéficié des conseils avisés de Denis. Je voudrais raconter l'histoire suivante. Donc j'avais été classé sur le poste de Nice au mois de mai 2009. Et suite à cela, l'université, enfin le laboratoire m'avait proposé de bénéficier pour l'année universitaire suivante d'un mois de prof invité. Donc je pouvais inviter qui je voulais, pour peu que ça satisfasse les critères de notoriété du laboratoire. Et il se trouve qu'au mois de juin de cette année-là, Denis organisait une conférence à Sofia, et donc j'étais allé le trouver pour avoir son avis et son opinion sur le sujet. Et il m'avait dit, écoute, il y a René Carmona qui va passer à cette conférence, pourquoi tu ne l'inviterais pas? Et c'est le début d'une autre belle histoire pour moi, et j'avais demandé à René s'il voulait venir, et par chance, je ne le connaissais pas, et par chance, il avait accepté de venir passer un mois à Nice. Et c'est à Denis que je le dois. Donc voilà, Denis a joué un grand rôle dans ce qu'a été ma carrière à Nice, et même ma vie, puisque j'ai fait ma vie à Nice suite à cela. Okay, so now let me switch to English. So the title of this talk is indeed the Rearranged Stochastic Heat Equation. So this is a bit mysterious title. I will try to explain what it means. And so this is based on joint works with these two people. The first one is William Hammersley, who is over there, a postdoc at University of Nice. And the second one is Youssef. I guess that many of you know Youssef from the University of Marrakech. So this is a distinct works with these two people, and I will say next what is the contribution of the two of them. So let me try to explain the basic motivation of this talk. So we had several times in this conference references to the smoothing effect of the Higgs kernel and the application to stochastic analysis, and we saw that in the talk of Stéphane this morning, and also in the talk of Milica on Tuesday. For instance, if you take an ordinary differential equation, so this one, and possibly with a velocity field that is singular, then you can enforce uniqueness by putting some noise. So this is a restoration of uniqueness phenomenon. And I know that this is well known in the audience. So the very basic question that I would like to raise, which is not exactly the question that I'm going to address next, but this is one of the motivation, is what about the same, but when instead of regarding this ordinary differential equation, you consider a Fokker-Planck equation. So now this is an infinite dimensional equation. The solution of it is a probability measure. There is no Laplace in this equation, and this has a role in the rest of the talk. So this is pretty simple in the sense that this is just a first order equation. And so you would like to say, well, is it possible to cook up a kind of noise under which, for sure, that the solution is becoming random, so the solution is going to be a random measure, but then you have some nice smoothing properties on the space of probability measures. So this is basically the idea that I would like to discuss. And I will try to give you some application to the notion of gradient descent on the space of probability measures, and also to mean field games. I hope that I will have time enough to do that. So intuitively, if you have to do this, you have to think about a kind of Brownian motion on the space of probability measures, which is certainly a difficult question. And to simplify my life, I will restrict myself to the case when the space is just one-dimensional. And you will see that even in this setting, this is not a trivial question. And in fact, there have been already several works about diffusion processes with values in the space of probability measures. You have, for instance, the Fleming-Veer processes, and there are very nice paper by Wilhelm Stannat about the smoothing properties of the Fleming-Veer process, and there's some kind of structure for it. There are some nice works by Sturm and von Renesse about the Wasserstand diffusion, also in dimension 1 based on the Dirichlet forms. This has been extended by geometric tools by Dello Schiavo quite recently, and some particle system approach by Konarowski. But in fact, at the end of the day, there is no canonical definition of what could be a Brunner motion on the space of probability measures, and somehow this leaves a space for other definitions or for other objects. And this is what I'm going to tell you in the next slides. So just to give a picture of the way it works, the inspiration is taken from the lecture, the very nice lectures by Lyons, Pierre-Louis Lyons at the Collège de France on mean-field games. And he had to study or to revisit the definition of differential calculus on the space of probability measures, which was very used in optimal transportation. And he had this very nice approach. So you take a function of a probability measure, and so phi of mu is the image, this is real valued, and you would like to define some derivatives. And what Lyons said is that, okay, when you have a space of probability measures, you can think of a space of random variables that lives on the top of the space of probability measures. And you can choose any probability space to have this space of random variables. So why not, for instance, to say that this is the space of random variables constructed on the torus equipped with the Lebesgue measure. And if you take a random variable in this L2 space, you map this random variable onto phi of the law of x. So the slight restriction when you do this is you just work with probability measure with a finite second moment. So you see that there is this subtlety in the notation that I put an index to say that any probability measures that I have now have a finite second order moment. And what Pierre-Louis said is that, okay, if you have this mapping now, this is defined on the Hilbert space, and you can have a look at the Fréchet derivative, and it turns out that the Fréchet derivative that you have is basically connected, and this is more or less the same as the Wasserstand derivative that people are using in optimal transportation. And so you could say, well, to think of a way to define a process acting on probability measures, why not to do the same? You just define a noise at the level of random variables, and somehow this could be a noise acting on probability measures. So do this very naively and then discuss whether this is meaningful or not. So you say, take your favorite example of a noise or process, a diffusion process with values in L2. And if you take the same mapping as before, you take a mapping phi of the law of a random variable, you could replace this random variable by the semigroup, for instance, of this Ornstein-Uhlenbeck process with values in L2. So once again, you have an SPDE, the solution of it is in L2, and you transport some initial condition, and you have a look at the law of it, and phi of the law of it. Well, it works, but this is bad, because if you do this, somehow you destroy the mean-field structure. You really feel the representative of your initial choice for the measure, for the probability measure, and even though you get some smoothing, you lose the mean-field structure of the problem, which is disappointing, because in mean-field models, you really want to benefit from the fact that this is mean-field, and so you have additional structure on the problem. And so this is the starting point of the notion of rearranged stochastic heat equation, which is based with joint work based with William. The idea is to say, okay, we keep this idea of doing some motion in the space of random variables, but we have to do that in such a way that this is mean-field or canonical in some sense. So there is a very nice way to do that. This is to do a splitting scheme. If you think in terms of numerical analysis, we heard about Euler schemes. So let's say that once again you have this equation. So this is the stochastic heat equation. Here W is a white noise. So for those of you who do not know exactly, you take the Fourier basis. This is on the torus, as I said before. And on each Fourier mode, you put a Brunner motion, and all of them are independent. And so this is the shape of the solution. And so the idea is as follows. You say, well, you make a small step in the Hilbert space of random variables, and you do some operation to project back onto the space of probability measures. So to try to keep something that is mean-field. And the way you can do this, this was discussed in another context by Brenier. He had to study some numerical schemes for some equation in fluid mechanics. And the tool that Brenier was using is to rearrange the solution. So you do one small step in the space of random variables, and you rearrange the solution. And you restart, you do a new step, and you rearrange, and you do a new step, and you rearrange, and so on. And so you could wonder whether you get a process when the time step here, this is dt, so intuitively this dt has to be really, really small. You could wonder whether you get something in the end, and what is or what are the probabilities of this something. And this is what I'm going to call the rearranged stochastic heat equation. So just a few words about the notion of rearrangement. I guess that all of you know this because this is something that is very classical in probability, but just to be sure, a few reminders about it. So if you take a probability measure on R, you know that this is canonically associated with the quantile function. So the quantile function is non-decreasing. And the very good point from a geometric point of view is that there is an isometry between the space of probability measures equipped with the Wasserstein distance. I'm not going to give the definition, but you know what the Wasserstein distance is. And the quantile function with the L2 norm. So when you make the difference between you compute the L2 norm of the difference between two quantile functions. So this is the same as the Wasserstein distance between the two laws which are behind. So this is absolutely meaningful from a geometric point of view to focus on the quantile function. And so conversely, if you have any random variable on the torus, you can say that you regard the law of it, and then you rearrange, and this is the rearrangement of your random variables. So which is to say that you replace your random variable by a non-decreasing version of it with the same distribution. The only subtlety is the notion of rearrangement on the torus. On the torus, what people are doing in analysis is that if you think of the torus as 0, 1, so I think this was, yes, this is 0, 1, you do something that is non-decreasing between 0 and 1/2, and then decreasing between 1/2 and 1. And this is a way to use periodicity in some estimates that I'm not going to discuss, but it gives additional estimates on the properties of the rearrangement. So just very, very simple picture to be sure that this is clear to all of you. If you get a random variable that is piecewise constant, so you see that this one is a piecewise constant random variable defined on the torus, and if you rearrange, so this is the way it works. So you have these intervals where this is constant, and you patch together the interval, and so you respect the length, the total length of the pre-images of your random variable. So this is the usual quantile, I would say, on 0, 1, and on the torus, what you do is that you make a contraction, so you pass this onto a 0, 1/2, and then you make a symmetry. So once again, this is a way to use periodicity of the torus, and so if you have some continuity, you avoid the fact that the quantile function could be non-continuous, which could be a drawback in Fourier analysis and so on. Okay, so this is the notion of rearrangement. So now you perform your scheme. You can design a kind of Euler scheme. I think this is a splitting scheme. So you alternate motion in the space of random variables and then rearrangement. So in these notations, H is a time. This is a time step. And so here you can forget the precise definition. This is just to say that this is one motion according to the free dynamics, the stochastic heat equation. And at the end of the time step, so you rearrange. So this is where you are at time n. This is one motion in the space L2, and you rearrange. And for sure, you wonder whether this is tight in some way. You would like to pass to the limit and get something. And the answer is that we are not able to do that, which is a pity in terms of application. I will mention this next. The reason is that at the level of the computation, the white noise is too singular to manage the computation. It seems that this is a surprise because you can define the stochastic heat equation without rearrangement in a nice way. But when you combine the heat summing group that is here and the rearrangement, you lose some properties, and we were not able with William to prove tightness. Okay, so this was a drawback. Just to say a word about the way it works, I don't want to be too technical, but this is just a word because this is the key inequality in the story. This is the one I mentioned before. This is what Brognier calls the non-expansion property of the rearrangement. So you take two random variables, u and v. The star is the rearrangement. So u and v, these are two random variables on the torus. And the L2 norm between the rearrangement is less than the L2 norm between the original random variable, which is exactly to say that it achieves some optimality in the optimal transportation that is behind. So this is exactly interpretation. And so in this kind of analysis, what you do is that you choose U star as the value of this, and V is equal to V star is basically the value of the scheme at a previous time step, and you try to use that and to iterate. This is the way Brenier did to address other problems, and we try to imitate this, but once again it failed. Okay, so this was rather disappointing for William and myself. And so we said, well, let us color the noise, which is a pity, but this was the only way we were able to proceed. So when you say color, it means that you put some decay on the Fourier coefficients. So on the higher Fourier coefficients, you see that you put these weights which are decaying according to some power law, and typically the exponent is lambda between 1/2 and 1. The fact that this is exactly m minus lambda does not play a role. What really matters is that asymptotically it behaves in this way. I'm not going to do the computation, but you can guess that now the noise is smoother, so certainly this is easier to do the analysis. And indeed, at the end of the day, after some computation, this is not easy. This is not a straightforward application of what you have without rearrangement. You have to work a little bit. Anyway, you get tightness. And the good part is that you preserve some smoothing for the free version. Because you could say, well, this is a bit disappointing to replace the white noise by a color noise, but we know from results, let's say by Daprato or the school by Daprato or other people, I don't know exactly, at least this is a book by Daprato, you preserve some smoothing effect. So for the free dynamics, so you can expect to preserve or to transfer those smoothing properties from the non-rearranged equation to the rearranged equation. Okay, anyway, we have tightness, and so this is a bit technical, but this is continuous from 0t into the L2 space. And so the limit should be a measure on this space. And so you wonder about what is the equation satisfied by the limit. This is a natural equation. So this is exactly what we call the rearranged equation. I guess that many of you know this, if you do this kind of scheme, so you alternate between Euler scheme and a kind of projection, because here this is exactly what you want to do. You project the L2 space onto the space of random variables. At the end of the day, you force the solution to live in a smaller subset. And so the limiting equation should be a reflected equation. So this is exactly what you have in the limit. So the type of equation that we obtain is this one. So once again, the unknown is a random variable. But the very good point is that this is a quantile function. So the unknown is a quantile function. So this is canonically associated with a probability measure. And so it makes sense to represent probability measures by this random variable and conversely. So this is the same structure as the heat equation, but plus a reflection. And so you have to study this equation or to say what is a solution to this. I have to say that for sure, there are some results about reflected SPDs, and I don't know where Etienne is. Anyway, there is a big result by Etienne, and there was Catherine Donati, David Mallard, and then also Lorenzo Tambotti did a lot about this, about reflection to SPDs with a white noise, but the constraint is to have a positive solution. And then you have some generalization by the team by Barbu, Rockner, and so on, who gave more general structural conditions to get a solution to this type of equation. But if you really have a look at this equation precisely with a reflection that forces the solution to be in a set of quantile functions, in a cone of quantile functions, so this was not applicable. So we had really to revisit the existing results. Very, very formally, I don't want to be too technical. This is just to give you some ideas about what we have been doing. What is this term? So this term, the eta, this is exactly the same as what you have in a reflected SDE. This is exactly the same. So this is a reflecting term. And so somehow this is the price you pay or the action that you have to put to force the solution to be in the right subset. So here, intuitively, this is the eta is after one infinitesimal step in the L2 space. This is the difference between the rearranged version and the non-rearranged version. And it turns out that this is one of the properties of rearrangement. So if you have a look at all the properties of rearrangement, so once again, this is very well explained by Brenier. if you take something that is the difference between rearranged and non-rearranged, and you test it with respect to something that is also non-decreasing, so that is a quantile function, then this has to be positive. And basically, this is the sign condition. So the sign condition that you have in reflected equation, in general, this is exactly that. So when you test this eta or d eta, so this is an infinitesimal step in this reflecting process against something that is non-decreasing, in the sense that on the torus this is decreasing and non-decreasing and then decreasing, then this is non-positive. It has to be smooth, so this U has to be smooth, because technically eta is just a distribution, so you have to be careful. You expand in Fourier, and you have to be sure that everything converges. Anyway, it makes sense. And at the end of the day, what you can say is that if you have a process z, or a path z, with values in the cone of quantile function, and those functions are smooth, then this integral is well defined, you can define it, and it has to be non-negative. So you have a definition of the reflection process. This is a bit by hand, but it seems to be fine. Okay, this is just to say that you expand in Fourier. This is not very important. And so at the end of the day, you have a notion of solution. So you have a notion of solution. So you say that to this rearranged stochastic equation, so you say that when tested with respect to smooth function, you should have the equation in a weak form, which is not a big surprise. And if you test this process eta with respect to things which are quantile or non-decreasing on the torus and smooth, so the reason why I put this modification is to be sure that this is smooth. The Higgs kernel preserves non-decreasing function on the torus, so this is absolutely listed to do that, so the sign has to be positive. And if you choose exactly z as the solution itself, which is indeed a quantile function by construction, then basically as the modification tends to 0, it has to be 0. So this is the usual orthogonality condition which you find in reflected SDs. So this is our notion of solution. We get a limit by letting h tend to 0 in the earlier scheme. And then you just have to prove uniqueness, but it turns out that once you have this list of conditions, you can completely duplicate the uniqueness proof for reflected SDEs in finite dimension, and this is the same, and you get uniqueness. Okay, so this is one thing, you have the equation. And now you wonder what to do with that. And so what we addressed with William is about the smoothing properties of this equation. So when I say smoothing properties, it means the smoothing properties of the semigroup. So the semigroup is going to act on functions defined on the space of probability measures. And this is really the objective. You want to modify function defined on the space of probability measures. So you can just rephrase if you switch to random variable. So basically you take a random variable, you rearrange to be sure that you start from the canonical representative of it. You have your dynamics, and now you take your any test function phi, you integrate this quantity. So this is really the semigroup that is inherited from those dynamics. And so when there is no reflection, this is something that we know. This is the solution is Gaussian, and so you know how to have a look at the smoothing properties. Here, this is more difficult because you have reflection, so you need a bit of stochastic analysis to do the computation. What we did with William is to adapt the Bismuth-Ellsworthy formula, but this is not so easy because of the reflection. Anyway, at the end of the day, we were able to prove that the semigroup maps L infinity function, so phi here is just an L infinity, into Lipschitz function. So here, the fact that this is Lipschitz, you can see that because you have a perturbation z of the initial condition, and you measure the perturbation with respect to L2. So once again, L2 here is associated with W2, the Wasserstein distance. So this is absolutely the right geometry. And you have some small time decay, a blow up. For sure it blows up in finite time. And this lambda, the one you have here, depends on the exponent in the power law, the fact that you have colored the noise. And so if you remember, I told you that lambda was very close to 1/2, above 1/2, but very close. And when you compute 1 plus lambda divided by 2, this is close to 3/4, which is very good in the sense that this is integrable. So in small time, this is something that is integrable, and this is one of the key things of the Higgs kernel to be integrable. This is not as good as t minus 1/2, but this is not so bad. No proof, I'm sorry about this. I prefer to discuss about possible application, but this is one result that we got with William. So this was something that we put on archive last year. And what we have been doing since is to see, well, some applications of this. And one possible application, which is purely theoretical at this stage, we could wonder about numerical meaning of this, but this is another story at this stage, is the application to gradient descent on the space of probability measures. There are more and more papers about minimizing functionals on the space of probability measures, and you could wonder about gradient descent. So let me try to make it quite simple. So you take a potential V. So V is a potential defined on the space of probability measures, and you would like to define or to have a look at the infimum or the minimum if you know that there is the infimum is attained. And to have a look at this, you could say, well, let's have a look at the gradient descent. And what is the gradient descent? Well, the gradient descent is this is a Mac-Inverse equation. So the gradient descent, so this is either you have a look at the descent in terms of probability measures, or you have a look at the descent in terms of random variables. And I guess that you understood that my point of view was to use random variables. So you have a look at the gradient descent in terms of a Mac-Inverse equation. So there is no noise here. There is no dB. This is a purely first order. So the randomness in the Mac-Inverse equation comes from the initial condition. So this is typically the shape of this of the gradient descent. So this is what we call the Wasserstein derivative of it. And I was mentioning the approach by Pierre-Louis for this derivative. I think this is very, very useful, and this was really an improvement in the understanding of this derivative. So the derivative of V is a function of the law, which is not a big surprise, but also of the realization of the random variable itself. So you compute the gradients at a given point in terms of the law of it and the realization of the random variable. And so if you work on the torus, so omega becomes little x and x is an element of the torus, this random variable, because this is a random variable computed at little x, this is exactly the Fréchet derivative of this big mapping that maps x onto V of the law of x. So you think of this big mapping, there is, under nice assumption, the Fréchet derivative. The Fréchet derivative, this is a random variable by the Riesz theorem. And so if you compute this derivative, this random variable at x, this is exactly that. Okay, and so the result by Pierre-Louis in the lecture, one of the results, is to prove that there is this representation, which is not straightforward. And Benjamin has a very nice paper about it. I don't know where Benjamin is. Okay. Anyway, back to the problem. You could say, well, what about forcing the descent by some noise? And I use exactly the same noise as the one I used before, which is to say that I put this reflected version of the stochastic equation. So now x is exactly the solution to the equation. So the motion. There is an additional drift in the motion, but except from this, the definition of the reflection is the same as before. So either you revisit the proof to say that there is a unique solution, or you just say that possibly you can apply Gersanoff theorem to say that there is a weak solution. Well, whatever. What really matters is whether there is something in long time, and what is the connection between the long time behavior and the original problem. This is what you should guess, or what you should wonder in this problem. Anyway, this is a big SDE. Just to illustrate, let's say that you take a potential that is of the following shape. So this is there is a nice smooth potential that is not too bad. So the functional is not too bad. I'm not going to precise the assumption. This is just to give you the idea. And we need a bit of a penalty. The penalty is here to constrain the descent, or the mean of the descent, not to go to infinity. So in fact, if you have a look at the descent, the stochastic descent, there could be a blow up in long time for the mean of the random variable. So for the mean, for the expectation of the random variable, or the mean of the probability measure. And if you put this additional confinement term, there is no problem. We can relax a little bit this condition, but this is, I think this is the typical kind of conditions that we should have. And then you have a unique invariant measure using the smoothing properties. So you can prove that there is a unique invariant measure to the dynamics. And now you could wonder about the shape of this invariant measure. Usually in stochastic gradient descent, you wonder about the connection between the invariant measure and the original minimization problem. And here there is a big disaster in some sense, which is that you don't have any explicit formula for the invariant measure, which was a big, this was a pity, and we were very, very disappointed about this. Usually what you expect is that the gradient descent has some Gibbs form. But in fact, the Gibbs form is, although we use it very frequently, this is very limited in terms of application because it requires the structure, the metric that governs the noise to be the same as the metric that governs the derivative. In fact, if you really have a look at the geometric condition, they must be the same to be sure that the invariant measure in the gradient descent is indeed a Gibbs measure. We don't have this, and the reason why we don't have this is basically because we're not able to use the white noise as a noise in the dynamics. If we were able to use the white noise, this would be wonderful, and our invariant measure, certainly this would be a Gibbs measure. But we're not able to do that because our noise is colored. So this was a bit disappointing for us. So we said, okay, let us try to see some metastability properties of the invariant measure when you put a very small noise, which is what you would like to do usually in stochastic descent. So let me give you quite simply the ideas. Once again, there is no statement. I apologize for this, but I thought this was easier just to have some pictures. So you put a small intensity in front of your noise. There should be a tilde. Anyway, the definition is here, but there should be a tilde. So you put a small intensity in terms of the noise, in terms of the friction, and you have to choose epsilon square if you choose epsilon here. And then in the noise, what you do is that you see that you have a colored noise, but it looks like a white noise when epsilon tends to zero. Because you see that the Fourier coefficients, this is just 1 times your Brownian motion here, up to the level minus epsilon minus 1. So it means that for many, many Fourier modes, this is exactly the same Fourier coefficients as the one you would have for a white noise. This is only for epsilon minus 1, very, very large, that you impose some decay on the Fourier modes. This is still fine. You still have a unique invariant measure for this equation, and you wonder about the shape of it. And this is our result. This is the best that we have now. Certainly, we could do better by large deviation from Hennenfent cell theory, but we have not studied that. Typically, if you have a look at a local well of the potential that is sufficiently convex, but locally, not globally, for sure, locally, and if you have a look at the exit time of this diffusion process from this local convex well, the mean time is exponential A divided by epsilon square, which is what you have usually in Hennenfent cell theory, and A is proportional to the height of the well, so which is exactly the result that you expect. So somehow the metastability properties of this descent are not completely stupid, and even though there is no Gibbs measure, or the invariant measure is not a Gibbs measure, this is not that stupid. So this is one first result of application, and I still have 5 minutes. Another result of application, which is, and this is another subject, and this is in fact the subject through which I came to this kind of question. This is for mean field games. I'm just going to recall quite briefly what a mean field game is. But just to say that in mean field game, before I give the proper definition, so we know a lot about existence of solutions to mean field games, but when you switch to uniqueness is a very, very difficult question in the sense that we know some classes of examples for which we have uniqueness, but quite often there is no uniqueness. And so here you can exactly wonder about restoration of uniqueness or forcing uniqueness by means of using a noise. And this was one of my motivations for addressing this question here. On simpler models, we had some positive results in this direction, proving that just with the help of some noise, you could enforce uniqueness to mean field games. Okay, let me just try to give you, this is also an example, just to illustrate what I'm doing. So in mean field games, what you are doing is that you optimize the state of one person in a collectivity of people, and you just describe this collectivity through the statistical state of it, okay? So you take one individual, there is no noise, once again, there is no BT in any of my models, in none of my models. And so you just tune the dynamics of this xt by the velocity. So alpha is a control, this is just in dimension 1, and this is the velocity, and you can choose the velocity. And with this particle, you assign a cost functional. For those of you who like stochastic control, this is very classical cost functional, so a terminal cost, running cost, and the energy that you are paying is just the square of the control. The only thing is that those coefficients G and F, they do depend on mu. What is mu? This is given. This is describing the state of some population that is around your person, that is around the individual. And you want to minimize. This is very easy. When u is fixed, you know how to minimize. I will tell you next the way it works. But in mean-field games, what you want is an equilibrium. So you want to find an environment mu such that the law of the optimizer is mu t itself. So this is a fixed point. So you take mu, you have a look at the law of the optimizer, and you want to match the environment and the output. Okay, just very quickly, assume that this is in dimension 1. So this is not a big model, but once again, this is one first result. You assume that f and g are convex in the direction x, in the measure nothing, in the direction x. The reason is that you would like to use Pontryagin principle to characterize the minimizers. And you know that under convexity, for sure, the critical points are also the minimizers. And so this is the Pontryagin system that you have. So the best drift or the best control is minus y, and y solves a backward equation. Here there is no stochasticity because the problem is without any noise at this step. The expectation is just under the initial condition. And mu t here, I said that I forced mu t to be the law of the solution. This is what I should have to get a solution to the mean-field game. I want mu t to be the law of the solution. So when you see Lebesgue S composed with x minus 1, it means that this is the law of x as a random variable defined on the torus with respect to the Lebesgue measure. So this is really the law of this random variable. So this is a Mac-Invasov system, and this Mac-Invasov system characterizes all the possible solutions to this mean-field game. But there could be plenty of them, okay? Under nice conditions on dxf and dxg, you could have existence. This is another story. Let me discuss about uniqueness. Once again, you may lose uniqueness very easily. And now you say, why not to put a noise? And so you put exactly the same noise as before. So once again, this is a the model becomes stochastic because of the presence of a noise, and you have to pay for a backward term, which is the theory of backward stochastic differential equation, and there are experts in the room. But this is the same system. And my claim is that, and this is what I've just done with Youssef. Now this is the part of the work with Youssef. There is a unique solution just because of the noise. And this is something that I did in my PhD thesis in finite dimension with Etienne to prove that in presence of a noise, you can restore uniqueness to forward-backward system. And here, this is exactly that, but on the space of probability measures. So this is one result, but the second result, which is very nice, is that in fact, if you have a look at the shape of the optimal feedback, this is what we call distributed shape, which means that to compute the value of yt, which is, so x is the randomness, and yt is the value of your control for this randomness. So this is a function, v, that is completely deterministic of your private state at time t. I'm sorry, I did two mistakes here, so there should be a t, and the parenthesis is not correct. So this is xt, and this is the law of the system. So to compute the optimal feedback, you just need to know where you are and what is the state of the collectivity, what is the state of the population. And there is no need to know precisely who is where and so on. No, I just need to know where I am sitting and what is the state of the population, which is the key property in the theory of mean-field games, because this is very cheap, somehow this is a cheap information to compute the optimal feedback. Okay, so I'm time. I'm done.
Any questions? Comments?
So when you were talking about this rescaled forcing of your equation, so I mean the typical regime, like, is it like some typical regime of this epsilon that you're interested in, or just here, like this?
Yeah, no, this is something that you tune the parameters, so you can fix the level of truncation somehow in the Fourier expansion of the noise. So you could have epsilon minus 2, epsilon minus 3, And you could, let me use the pointer, this would be easier. So I think that your question is there any relation between this -1 and this +1 and this +2?
Yeah,
and the answer is yes, indeed. If you choose something else, certainly the result won't be this one. So I completely agree that you do the computation, you put some parameters, some exponent, you choose, and at the end of the day, you realize that this is for this choice that you have the metastability result, which is completely theoretical. So maybe at the end of the day, this would be absolutely wonderful to see whether we can have something from a numerical point of view. Etienne and William are studying some scheme, but this is another question. But the answer is yes, there is a precise choice of parameters. Thank you.
Do you have any idea how to go to higher dimension?
To prove?
Est-ce que tu as une idée pour aller avec les équations posées en dimension?
Ah, yes, yes. Okay, so this is a very good question indeed. So in higher dimension, so my first idea was to use optimal transportation. But in fact, I think this is a bad idea. I discussed with Filippo Sant'Ambrogio, and he told me that indeed there were some results, but this was a disaster from a complexity point of view. And so in fact, I think that but I have not started to do that. I would like to do this with some of the young people in the room, to do a kind of triangular coupling. So you start with the first coordinate, you have the quantile, and then you do the quantile for the second one given the first one. And I think, I'm not sure about it, but I think that this triangular structure could be fine, and numerically, or in terms of complexity, maybe this could be affordable. I don't know yet, but this is the way I think we will try to do that.
Any other question? Okay, so let's thank François again. Thank you. We have a break.